So let's look at type 1, which is growth decay models. So as usual, I'm going to maybe take beef with the guided notes or the way the book does it. They act as if growth and decay models are two different things. And they even write them slightly differently. They're the exact same model, the exact same thing. The difference is what your growth constant is. Okay, so a population that follows exponential growth can be described using this function. P of t equals p naught a to the t, and so this is a function that takes in a time and is going to spit out population at that time. So this is not p times t. This is the population function with the input t. P naught is the initial population and a is the growth constant. So off the side here, p sub 0, this is a subscript, this is not times, this is a subscript, and it's read as p naught, N-O-U-G-H-T, like saying that something is all for naught, meaning nothing, right? So naught is another word for 0. So this is p naught. A is the growth constant. If your A is something between 0, 1, so like a half, then as you raise it to larger powers, it actually gets smaller. So that means that your population would be decaying. So the only thing that separates a growth model from a decay model is if A is less than 1 or bigger than 1. That's it. Okay, now I use the word population here very loosely. Population, it doesn't mean people. It doesn't even mean living things. It could be atoms in a sample. It could be money somehow if you have like exponential wealth growth. Okay, so I'm using the word population here very loosely. The initial population means how much you start with. Whatever your population is, how much you start with is your P naught. Okay, so let's look at an example of a growth or decay model. So here's my first example. A certain population of rabbits follows an exponential growth with this function. So P of t is 3 times 2.4 to the t, where t is in months. What is the population after 4 months? What is the population after 2 years? And then I actually put a question that technically we cannot solve yet, but once we get to 7.5 we will be able to solve. When will the population be 39 rabbits? And I'm going to talk about that question, though I won't show you how we solve for it, but I will talk about it so that when we get to 7.5, we know how we would solve it. Okay, so population after 4 months. So if I want to do that, I'm saying, so this function, actually, even before I solve, let's talk about it. The P function takes in months and spits out number of rabbits. That's what it does. So in will go months, out will come number of rabbits. All right. So if I want A, what's the population after 4 months? So that means in to my function, I'm going to plug 4. So t equals 4 means I do p at 4. Which gives me this, and this is calculator. So I get my calculator out, I do 3 times, actually I think I need to write the times, 2.4 to the 4th power. 99.5. So I have 99.5 rabbits after 4 months. Now, usually in word problems like this, I'd ask you to round to the nearest rabbit, so you could put 100 rabbits. Okay. This 3, by the way, is our P0. So I start with 3 rabbits, and after 4 months, I have 100 rabbits. So how many rabbits am I going to have after 2 years? So for 2 years, my P function has to take in months. Years is not months, so I need to turn that into months, which means I would have 24 months. So that means I'm doing P at 24. Just 3 times 2.4 to the 24. Can my calculator do that? I don't know. Hope so. Yes, it can. Okay, good. I don't even need scientific notation. So this is 40012073331. Right? So 4,1,207,331 rabbits. So a common error that I see in this section is students will say, well, in 4 months it went from 3 to 100, so 24 months is 6 times that, so it'd be 6 times as big, right? So you'd have like 600 rabbits or whatever. The issue with that thinking is you're assuming that it's always increasing at exactly the same rate, that it's linearly increasing. It's not linear. If it were linear, I wouldn't need an exponential function. I wouldn't be doing this section. We would have done this back in chapter 2. This isn't linear, it's exponential. It's growing faster as time goes on. So just because 4 months, let me say, just because 24 months is 6 times as long as 4 months, this does not mean that the population will be 6 times as large. That's missing the whole point of this section. The whole point of this section is that you can't do this. That's why we're doing exponential. As I get more rabbits, it's growing quicker. So it takes 4 months to go from 3 to 99, which is an increase of 100, basically, an increase of 100, basically. If I plug in 6, so now 6 months, now I'm at 573. So in 4 months, I got 100 rabbits. In another 2 months, I gained 400 more rabbits because I'm doing 2.4 to a power. So this is more than doubling every month. If I were able to just take, oh, well, just multiply this thing by 6, we would not be in the exponential function section. That would be linear. So you absolutely cannot make this sort of deduction. This is the opposite of what an exponential function is. The more you have, the faster it grows. You're getting this feedback loop into your function with this exponential growth. So I said I was going to talk about C. We're not going to do C because we don't have the capability of doing it yet, but I just want to talk about it. So what is the population? So if I'm asking what is a population, then I'm going to be looking for a P of T. I'm going to be given a time, and I want to know a population. When will the population be 39 rabbits? So that means I have a number of rabbits, and I'm looking for a time. So I'm going to be solving for a T trapped inside of an exponent. And we don't have the capabilities of solving this specific C right now. I mean, we kind of did this back in 7.1 a little bit, where we solved for a variable and an exponent. But it only when it was very specific, only when you were able to write both sides as the same base to an exponent. I can't necessarily do that here. So in 7.5 we will learn how to solve the question, when will the population be 39? Which, by the way, we know that in 4 months it's 99, so it has to be less than 4, right? It has to be like, I don't know, 2 months maybe? Maybe 2 months? All right.